good afternoon to people in the US and might be good evening at other places. I am Dr. D.K. Panda from X-ScaleSolutions. I am the founder and CEO of X-ScaleSolutions. I am also a professor at the Ohio State University. And together with me, my co-speaker, Dr. Donglai Dai. He is the chief engineer at the X-ScaleSolutions. So two of us today will be presenting this talk, which is titled High Performance and Scalable Middleware for HPC and Deep Learning on OpenPOWER platforms. So to start the talk, I'll quickly provide a short overview of the X-ScaleSolutions companies. And both from the X-ScaleSolutions side and also Ohio State University, we have been working with OpenPOWER consortium for many years. And especially from the company perspective, we have several products here. X-Scale HPC, X-Scale AI. There is a new MVAPICH2 DPU, which is especially focusing on the NVIDIA's new DPU technology. And a fourth project, which is SCR-EXA, which is Scalable Checkpoint Restart Tool for HPC and DL applications. So we'll try to go over all these four products and trying to show some of the performance and scalability numbers, what you can especially achieve from OpenPOWER platforms. Then we'll conclude the talk and we'll have a question and answer session. And especially as we present, if you have any questions, please feel free to ask in the chat, or alternatively, you can unmute yourself and just raise your hand, and then we'll be very happy to talk directly. So just to bring an overview of the X-ScaleSolutions. So this is a company which was formed around 4 years back. And this is a commercial spin-off based on the activities, what has happened over the years at the Ohio State University, especially on cluster computing, supercomputing, HPC and deep learning. I have been leading a very large group at the Ohio State University for many years. And one of the major products from OSU has been the MVAPICH2 MPI library. Some of you might be familiar. It actually drives a lot of top 500 systems, not only OpenPOWER, but also x86. And the other one, whatever has been also available from the Ohio State University, is the high performance big data libraries like Hadoop, Spark, HBase, Memcached, all being enabled with the RDMA version. So one of the primary objectives of this company has been to provide commercial support. That's how the company started. And through that commercial support agreement, we have been able to support many organizations, just like any other commercial vendors, trying to provide high performance middleware, both on the HPC side, deep learning side, big data side, to the end customers. And of course, the commercial support includes different kinds of service level agreements. It also includes platform specific optimizations, applications level optimizations, whatever is available on top of things being available from the Ohio State University side. But over the years, as the company has been growing, we have actually trying to add value-added products, okay, or value-added features, value-added enhancements, and this is what I'll be talking a little bit more into details. And we are winner of multiple US Department of Energy, SBI grants to design and develop such innovative and value-added products. And then we market these products both for HPC as well as AI applications with commercial support. And for many years, X-ScaleSolutions as well as Ohio State University has been silver ISB members of the OpenPOWER consortium. So with that kind of a short background, let me go into our details of the products. I'll start with the X-Scale HPC, which is very high performance optimized solutions for pure HPC applications. So as I indicated, the Ohio State University has been, the MVAPICH2 MPI library has been, this project has been running for 20 years. We started almost day one of InfiniBand. When it started in October 2000, we had the very first release of our library at the supercomputing O2, almost 19 years back. And since then, it has been growing. And currently, we have more than like 3,000 organizations. They are utilizing this software stack purely this is from the OSU open source side. And from the OSU side also, we crossed almost 1.5 million downloads we have crossed. So what here X-Scale HPC does, it actually takes that the open source solution, but it is very fine-tuned, okay? Because as you know, these days the clusters come in all different shapes and sizes, all different CPU speed, all different GPU speed, number of GPUs per node might be different, all different kinds of interconnects. So the X-Scale HPC takes care of a lot of this fine-tuning and optimal performance so that you can directly, as soon as you install it on a system, you should be able to get the best performance. So I'll try to show some numbers here, performance numbers. So these are the numbers has been taken from a GPU cluster. This is on the, you can say like this is the POWER9 system equipped with a dual socket CPU, 4 volt V100 GPUs, and 2-port EDR, InfiniBand interconnect. So now you can see like a intra-node latency. This is like we are talking device to device. That means the GPUs which are on the same node. Think of like a GPU to GPU communication. We can achieve actually in 800 nanosecond. In fact, the exact number is 760 nanoseconds. And here we utilize actually the NVIDIA/Mellanox, the GPU Direct RDMA, GDR copy, a lot of those features to give this kind of a very low latency. And that also carries out to even for very large messages. You can see even 4 megabyte messages, we can actually communicate it around in 78 microseconds. And we give very high bandwidth, especially for systems. These are the systems kind like the SUMMIT, Sierra, Lassen, a lot of the OpenPOWER deployments, which have been already running for many years. As you can see here, via NVLink 2, we are able to deliver almost 65 gigabytes per second, GPU to GPU bandwidth. And in the internode is also very impressive. As you can see here, this number is 2.18 microseconds. So that is from GPU to GPU over the network, okay, over the InfiniBand. So it's not host to host. Host to host InfiniBand these days is around 1 microsecond. And here, this is also OpenPOWER. So that is a little bit like it takes additional time compared to an x86 platform. So here we are able to deliver around 2.18 microsecond. And as you can see, the internode bandwidth, we are able to get almost 23 gigabytes per second. This is the 2-port EDR. So that shows the powerfulness of this package, and it is out of the box. As I said, you should be able to use and install these to get this kind of numbers. So this is another number which we ran on the, this is our MVAPICH2-GDR, which is the GPU Direct RDMA, which is very optimized for GPU-based clusters with OpenPOWER. And these numbers have been taken with OSU SUMMIT. As you know, OSU SUMMIT is an OpenPOWER system with InfiniBand. It has been the #1 system for many years, and last year it got to #2. So here you can see one such collective, which is called MPI all reduce. Many of you might be knowing MPI all reduce is heavily used both on the HPC side as well as the deep learning. And here we are comparing MPI all reduce performance in MVAPICH2-GDR with the Nickel library from NVIDIA. And here, as you can see, we are able to scale to almost 1536 GPUs. In fact, these results were all presented at ICS 2020. You can take a look at the details from there, from this paper. And these numbers were from July 2020 from the papers I am referring. As you can see, like, so here, like the light black line, latency-wise, we were able to deliver better. Even the large messages bandwidth, we are able to deliver better. And as you can see, the number of GPUs, as we are scaling, in fact, we are able to get in very good numbers compared to in the other competing libraries, MPI libraries like Spectrum MPI, OpenMPI, and Nickel 2.6. So not only like those are the point-to-point communication and collective, but we also have a lot of optimizations on data types. As you know, many HPC applications, and recently also a lot of deep learning applications are trying to head into that. They are using a lot of data types, or in the deep learning terminology, those are tensors. And so how to optimize those? So this is where here we are taking an application like Milk. That's the communication kernel. Again, these results were presented in the HPC 2019. And what we are showing here is the proposed, that was like a 2009 December. but these are all available in the latest X-ScaleHPC package. So here you can see the mill communication kernel. We are able to provide the speed up. These are the different problem sizes. We are able to push the performance up to 4.3x. And so here it is like the Jacobi, which is another 2D stencil computation. Similar kind of things. We are able to improve performance by 13%. And if you see here, Cosmo model, which is a weather forecasting model, we are able to reduce the execution time. This has been taken on the Cray CS Storm platform. This is from the CSCS Supercomputing Center in Switzerland. We are able to improve the performance by a factor of almost 15x and 3.4x. So that just shows the highlight of this basic X-ScaleHPC package purely for targeted for HPC. Now, based on that, we have also moved ahead to the second product, which is the X-ScaleAI. And this especially focuses on high performance solutions for the deep learning and AI applications. And a new thing which is included here is called deep introspection. I'll spend some time going over that in detail. So as you know, these days, I mean, there is a lot of synergistic things that are happening between HPC and AI. People are trying to, a lot of AI applications, like if you take deep learning, machine learning, data science, they want to actually utilize HPC platforms. And HPC platform, new generation of HPC platforms are being designed to deliver really the performance for these AI applications. So in that context, our goal is to really provide this middleware, which can be deployed on any of the OpenPOWER platforms, including also x86 and even ARM. And end users should be able to not only directly take advantage of it out of the box, but they can also do performance engineering. Okay, I'll go into that more details. So these are all the major features. These are easy to use, deployment and execution, again, out of the box. We try to support a lot of different combinations of compute platforms, networks, as well as GPUs. Delivers high performance, scalability to thousands of GPUs. I'll show you these numbers. The other thing is, which is very important, which is you never see in any other stacks, is the deep introspection capabilities with visualization support. Okay? So for example, imagine there's an end data scientist trying to run a big model, some ResNet 1000 or one of those models with, let's say, PyTorch or TensorFlow on a 2000 node GPU systems. How do you know that that user is getting the best performance? Okay, many times what happens is end data scientists don't have a lot of understanding on what is happening in within the system. And we have a specialized tool here through visualization support. You will be able to get information saying, is there some performance issues exist? And if those performance issues exist, how to debug, how do you carry out additional tuning and then optimization so that you can boost your performance. So that is there available in this package. So this is again built on the top of the Ohio State University's the MVAPICH2 libraries, leveraging excellent performance and scalability. So we have done a very tight integration with major deep learning frameworks like TensorFlow, PyTorch, MemXNet, and also a lot of intermediate middleware. Some of you might have heard of Horovod, DeepSpeed, distributed PyTorch. So those kind of middlewares are also integrated. So you don't need any additional communication library to run our thing. So it has all the components and the end users don't have to make any changes. For example, if you have some installations with ResNet 50 running with TensorFlow, or the end user is trying to use TensorFlow or PyTorch on a GPU-based system with OpenPOWER, might be using Nickel library, but instead of that, you can actually use our X-ScaleAI, and then you will be able to get better performance. I'll show it to you. Better performance and better scalability compared to what you have been using. And on top of that, you will be able to get this integrated profiling and introspection support in a visualization manner, and it will help the users as well as the system administrators to make sure that you are actually harnessing the best performance and scalability. And this is targeted for both CPU-based system as well as GPU-based system, out-of-the-box optimal performance, one-click deployment. And as I indicated earlier, we try to support a lot of different platforms. Here I'm outlining OpenPOWER and x86. It also supports all the different interconnect like InfiniBand, Rocky, and NVIDIA. So here's some numbers here. This is again taken on the Summit system. So this is the ScaleAI trying to utilize the distributed TensorFlow. And as you can see, it is 1536 GPUs we are trying to run here. And this is running ResNet 50 using TensorFlow. And then here we have used ImageNet 1K. It has 1.2 million images. And as you can see, as the number of GPUs have been increasing compared to the Nickel library, we're able to in fact scale very nicely, even up to 1536 GPUs. And as you can see, we are able to deliver almost like a 0.42 million images per second. If you do an estimation, the entire thing we are able to train in just 4.5 minutes. Okay, using 1500 GPUs, we are able to get this kind of performance. Now, this is what shows the overview of the our deep introspection support. It is just like think of like you are driving a car, just like we have the dashboard. At many times, if there is a problem, I mean, you will get the dashboard tells you, okay, how many miles per speed you are going, what is the RPM, if the engine is cool or if it is getting heated up. So you get everything in one dashboard. So that's what we have done here. So we call it a deep introspect profiler. And it has a lot of drop-down menu. As the job is running, you can actually get live data, okay, of what is happening. So for example, for a lot of deep learning applications, whether you are using data parallelism or model parallelism or hybrid parallelism, the performance of one such collective called all reduce, which is very important. So in this case, we are trying to, let's say, narrow down to saying, as the job is running, is your MPI all reduce running in the best possible manner? Because if that is not running well, then you will be not getting the best performance. So that's what it's trying to do. MPI all reduce, so it tells exactly, you see how many calls are being made, how much total time it is taking. And then the more important thing is trying to show, as you can see here, distribution of what kind of message sizes were used as the job was running. Here it says like a average message sizes like a this much time it was taking. This is the average, this is the mean max of a 685 kilobytes of message. Okay, so like this, it gives you the complete distribution. And then here you can see it shows you in a pictorial analysis. And as you can see very quickly, if somebody takes a look at these numbers as the job is running, you will see that, oh, the library or the underlying software stack is not optimized in this region. Okay? Because as you can see, for higher message sizes, we are getting very good performance, but for smaller message sizes, we are not getting the performance. Same thing here, it says like a MPI all reduce count by message sizes. So that means it is telling you that in this particular, while we are running this model on this system, message sizes of these sizes are very important. So like this, you can get a lot of information and it will tell you, okay, go ahead and try to optimize the library or something has gone wrong here. And if we can fix that, we'll be able to get even better performance. So just to illustrate that concept further, here I'll try to show two use cases. We work with some users trying to see how this tool together with the XScaleAI package can actually help you. Okay? So here this user one was running Horovod with our MVAPICH2-GDR with the training. And this bar, this is the kind of performance it was trying to get. Okay? But then the ideal scaling for a given system, you know, depending on the GPU performance, the system size, you can actually get some rough idea of how many images per second you will be able to get. So as you can see, there was a big gap here. And through the tool, we are able to actually help the user to find out where the bottleneck could be happening. And in this case, it was happening in the Horovod. The Horovod layer, as you know, Horovod has a lot of parameters. And we were able to nail down some particular parameters which was not set properly here. And after we took care of this, we are able to push the performance almost by 30%. And for all these GPUs, we are able to come very close to ideal scaling. Of course, you never get the ideal scaling in a parallel environment, but here we are able to push the performance 30% higher. And then this is just using this tool. In the absence of the tools, of course, one can try to do the same thing, but it will take you some time depending on the experience of the end user or the system administrator or the developers. It may take you from weeks to months. Okay? Whereas by using our tool, you are able to, in a few hours, you are able to fix this and then deliver your performance. And if your job training, like you can get better 30% performance, now you can think that this will trying to reduce your training time by 30%. And that gives you a lot of cost performance advantage, even on the on-premise system as well as on the cloud system, because these packages are also available for the cloud. So this is another one on the user case too. Similar kind of things. We worked with this user. The user was using ResNet 50, and same thing. So this number, as you can see, it is running on 1,000 GPUs. And especially when you are running these kind of jobs on very large scale GPUs, performance debugging is very hard. Okay? If some of you are familiar with how you try to analyze the thing, I mean, it's not like a 1 or 2 GPUs, 1,000 GPUs. So a lot of interactions are happening underlying the system stack. So you need to have some kind of this kind of a visualization, deep introspection, which will actually help you to see what is happening. So the user was expecting 370,000 images per second, but what it was actually getting in the beginning, 181,000. The job was almost running with half the speed, okay? Whereas after using our tool and trying to fix it, the user was able to come very close to, like you can see, 341, 590 images per second. So we were able to deliver like a 1.9x speed up using our tool. So in summary, this particular one is very much geared towards, this product is for the OpenPOWER platform with InfiniBand, and especially to extract high performance AI. So it is very easy to use in terms of deployment and execution, delivers good performance, scalability, and deep introspection capabilities with visualization and support helps you actually to really go into the bare metal performance from your underlying system. So let me indicate the third one. So this is a very new product we have introduced. Currently, it is being done with x86. I'll show some results with x86, but conceptually, it will also work with OpenPOWER. The only thing is that there is no deployment yet with OpenPOWER and DPU. But as long as if you have, or if you are considering any such platform, our solution should be able to help you there. So the broad idea is that if some of you are familiar with what is happening, the DPU stands for like the data center processing unit. In the earlier days, the InfiniBand, let's say from Mellanox, and has been only providing RDMA capabilities and with a lot of features. So that's how a lot of these InfiniBand clusters are utilizing this. But now these adapters are being enhanced with additional features like providing even ARM cores, programmable ARM cores on the network adapter itself. Okay, so that is the next phase which is coming up. So this is the architecture of a Bluefield DPU, 2 DPU. So you can see these are like the host servers, and this is your network. So in this context, we have like a 64-bit ARM V8, A72 cores with a 2 GHz, and it has 16 gigabytes of memory. And then this is a ConnectX-6 with SDR200 is running there. And these are the hosts. So now you can see the scenario when you have this kind of intelligent network adapter. Imagine how our typical corporate environment works. In a typical corporate environment, you will see that there are a lot of executives, but there are also a lot of secretaries to actually help the executive to offload a lot of things, okay? So that the executives don't have to spend a lot of time on things which can be offloaded, and they can focus on important things. So think of like, let's say you want to set up a video meeting with 50 people. Of course, the executive can do it, but the executive a lot of time will be spent. So then he or she tells the secretary saying, yeah, please, these are the list. Go ahead and find out a common time, set up the video call, and then a Zoom call, and let me know. Okay? So that means we are offloading those tasks from the executive to the secretary. So the same idea here, we started asking how we can try to redesign an MPI library, because the MPI library, the message passing interface, as I've been telling, is very important. You need a very good environment or a very good solution to provide high performance and scalability. So here we ask the question, how you can take advantage of the DPUs and accelerate actually scientific applications. So we have already done initial work. This is already available as we call it MVAPICH2 DPU library. Again, it is derived from MVAPICH2, OSU open source MVAPICH2. But inside that, it has all the supports, let's say up to the latest MVAPICH2 236 release. But it has now, as of now, the second release, what we have made here, it has support for some non-blocking collectives. So let me introduce, if you are not familiar, in the MPI context, there will be a lot of collective communication. I introduced all reduce earlier, but you can say all to all gather, bcast. So these are the collectives which exchanges a lot of information or the data. So in the older days of the MPI standard, these used to be blocking. So that means if I want to do an all to all, like I have computation done, then I do all to all. While the communication is taking place, my CPUs are idle because they are not able to make progress. Or sometimes what happens, depending on how the all to all algorithm is implemented, the CPUs participate in making some communication progress. So they are not really spending time with in the computation. So that doesn't actually work very well when you are trying to scale the job. So the question is, can I do it in an overlapped fashion, computation with communication? And this is where the MPI 3 standard introduced I all to all. That means non-blocking all to all, or similarly I all gather, I bcast. So the idea is that if I have some computations done, I can introduce all to all, and while all to all is taking place, if I have some other computations to be done, I can actually continue with that. Okay? And then come back and check whether the new data is available, and then I go to the next stage. Okay? So simple example I tell my student is just like you are waiting for your friends to come to your house, and then you can go to a movie. But then while your friend is coming, the question is, what are you doing? If you are not doing anything and just continuously waiting for the friend to come, that is blocking. But then that doesn't make you very productive. On the other hand, while your friend is coming, if you can do your own work, that means you are able to overlap your work with your friend coming, and then it will give you the boost in performance and productivity. So that is the concept we are trying to bring here. So let me show you some concrete numbers. So these experiments have been run with the latest MVAPICH2 DPU package. Here we are trying to show on this left-hand side, 32 node 16 PPN, like a 512 process experiment, and the right-hand side is 1024 process experiments. And as you can see, this is the red bar. Here you can see, especially in the basic MVAPICH2, when you are trying to do the non-blocking, as I indicated earlier, for the non-blocking, the CPUs themselves have to extend help in the progress of communication. Okay, so that's why you don't see any overlap between computation and communication. Those are very small. But as soon as you offload that, so these ARM processors are continuously communicating with each themselves to implement that all to all. So that gives us very good overlap, like 100% overlap. Okay? So now if you try to run it with computation, so here we are using the standard OSU micro benchmark, which is a part of the MVAPICH2 library. It has been there for the last 20 years. A lot of people in the community report numbers with that. Here you can see we are trying to do this, the structure, as I indicated earlier, like we initiate a non-blocking all to all, and while we are trying to do the computation. Okay? So especially in the basic MVAPICH2, since they cannot be overlapped, it takes more time. But now with the new MVAPICH2 DPU library, since they can be overlapped, as you can see here, this is an all to all with a 512 kilobytes of message exchange. Now I can show benefits of 22%. Okay, because of this new offloaded design. Same thing here also with a 17% on 1024 processes. So that is just at the micro benchmarks layer. But what happens to the application? So in this case, actually, in order to take advantage of this new paradigm, just like I gave an example of, you need to, if you want to get really overlap while your friend is coming, you need to think of what I need to work during the time my friend is coming. So that means my application has to be restructured. So here we work, one of the application developers of the P3D FFT. As you know, the FFT is a very dense operation with a lot of all-to-all. So there is a library called P3D FFT from SDSC, San Diego Supercomputing Center. We worked with the developer, and the developer was able to restructure that application. And now if we run, so this is the real application which is running on 512 process here with 1,000 process here, and these are the 3D grids, like a 2K by 2K by 2K. And at the application level, now you can see 12%, 18%, 21%, we are able to show the benefit. Okay, so it's the same hardware, but now we are able to take advantage of the hardware capability to really speed up the application. And that clearly shows the cost performance benefit. For example, if I get like a 21% benefit in my application execution time, if the new DPU technology is taking 10% higher cost than the previous one, then you are a winner here, okay, using the MVAPICH2 DPU. Similar kind of things here we have done for IAllGather, that is another collective. Similar things here, you will see a 41%, 48% kind of benefit. And we took another example is radix sort. Sorting is very common. So that utilizes an IAllGather. So this is the very first sort version we have done, but still we have see like around 7% performance improvement at the application level, which is not very easy to achieve these days when a lot of optimizations are taking place at all levels. And we are continuously rewriting that radix sort, and hopefully we'll be able to get even better performance. And then this is the final one is the IBcast, which is the broadcast, non-blocking broadcast. Again, as you can see here, when we add we do the broadcast, and at the same time, we are also trying to overlap with computation, we are able to get 59%, 60% benefit. Okay? And we are working on the associated application also. So in this context, so this is a very new paradigm which we have been introducing. As I said, these are all x86 numbers. But if there is an OpenPOWER platform and any one of you are deploying with the DPU technology, we'll be very happy to work with you. And especially if some of your applications are using non-blocking collectives, we'll also be very happy to work with you to really demonstrate the performance and scalability at the application level. So the final product here, I'll try to hand it over to my co-speaker, Dr. Donglai Dai, which is titled SCR-EXA, which is a scalable checkpoint restart tool for HPC and DL applications.
Okay.
Donglai, you can get started.
So I'm going to introduce this one, SCR-EXA. Okay, this is the new product we're going to bring into the market. And this itself is built on top of open source SCR library. And by the way, this library has been used and developed by the Livermore National Lab for more than a decade. And it has been proving very effective for their daily workload. And so we take this to extend it, the reach, where it can be used, as well as to provide commercial support. More importantly, we try to extend it to new applications like a DL, as well as to put into cloud environment. So in overall, we are going to add new features as well as functions on top of the open source. However, some part of the functionality we added, if it's appropriate, we're going to contribute back to the open source so that it's open. And other people can also leverage from the open source. And also, as I indicated, we're going to customize as well as optimize for a diverse range of systems schedulers way beyond the National Research Lab in Livermore. Okay. Next. Okay, so this one I'll spend a little bit of time to explain. So what we did in this product for extension is we try to, as I indicated, we try to extend it to deep learning applications. Our approach is we will make it generic, this kind of thing, generic of enablement, so that most of the applications you use certain DL platforms. If we instrument as well as enable at the platform level, then any applications, or at least most of the applications, use the deep learning platforms without much of a modification, can be directly leveraged and take advantage of our enablement. Okay, and specifically for this, currently we're going to show two different platforms that have been enabled and evaluated. We're going to show the benefit as well as effectiveness. And particularly in this presentation, we're going to show Horovod as well as PyTorch distributed module. Okay, Horovod here will only show the Horovod support for PyTorch. And if you have used that PyTorch in the past, you know that there is a built-in, by default, actually released checkpoint scheme exists in that PyTorch open source. Okay, we call it slightly naive because it does not take advantage of more advanced features for checkpointing. And also we are going to show what SCR-XR can help us in certain ways so that this becomes more powerful as well as can be adopted widely, okay? And as you know that in the deep learning, especially like PyTorch, this kind of thing, as well as Tensor, most of this are doing the iterative learning experiments. It means forward propagation as well as backward propagation. And what happens is during the backward propagation, all the learning for the model is get broadcast to all the different models on different nodes so that they can be carried out, built on top of that. And the accuracy of the model gets improved. And to take advantage of this feature, so we took the checkpoint is every time we doing the backward propagation where we sync up all the models on different nodes so that they are using the exactly same model for next epoch, okay? And at this point, we can take a checkpoint and so that it's reduced the amount of data as well as it's a clean separation, okay? Separation of state, especially with a GPU type of thing, where you have accelerators. And as you sync, at this sync point, all the intermediate state in the data as well as the queue jobs can be captured from the CPU perspective. Okay, so this is, at this particular task or evaluation point, we're going to show that we're taking a checkpoint for each of the epoch or epoch, okay? And we're going to show, as you can see on the data on the left, okay, we're going to show 3 bars. One is without activate the checkpoint. That's the red bar. Then the other one is the naive or the built-in scheme, okay, the green bar, as well as the SCR-XR checkpoint, which is a blue bar. And as you can see, we use as the number of GPUs we use for the application increase. And initially, the blue bar is higher than the green bar a little bit, okay? However, as you scale it up, and the blue bar actually outperform the green bar. But overall, the overhead is potentially perceivable, okay? But because what happens is that the overhead, it depends on how many times you do the real checkpoint. And that can be adjusted by the application as well as by our scheme, okay? Based on your actually fault model, you know, how much you're running typically without a failure, then you can treat that off, okay? But here we're going to show the effect as we take the checkpoint at every epoch so that we can see the effectiveness. And you can see on the right part side where you can see the overhead. Here, the scaling is, the naive ones is somewhat linear, okay, to the size of your application or your system running on, okay? And of course, at certain point, it may not become linear, but still the overhead is really increasing on the overall system size. However, on the SCR-XR, it's more or less flattened, okay? It's controllable. And the reason is because what is the uniqueness of the SCR design itself, SCR-XR design itself. One is it's used multiple level of storage, okay? So that you can use most of your stuff, checkpoint related files stored on your local storage. And the backup from the local to the global shared file system can be done based on whatever frequency feel like enough to cover the fault, the system fault in certain way. And for this particular test, we evaluate, we set the parameter to as a 10. Okay, so every 1 out of the 10 epoch of whatever you take the local on the local storage, you're going to move it to back it up to the shared system, shared file, global file system. And in addition to that, this backup is done asynchronously. So it's not part of your application performance is not affected by it. That's why you can see this, why the effective is so dramatic. Okay, next. And this is another application. Oh no, sorry. This is using the Horovod platform, using Horovod on PyTorch. And as you can see, the trend is very similar. Okay, the numbers may different in the margins of that, but the trend is very similar. So what we state is the effectiveness of SCR XR is make it very scalable. Okay, and as we can say that the overhead actually it depends on how often you need to take the checkpoint, which we can be adjusted based on your fault model as well as whatever the time to failure that can. Okay. So by the way, this is, we only use a ResNet to show this. We actually have other applications just to prove the point that whatever we have done on the platform, I mean the DL platform, okay, that one is actually can be applicable to other applications, not just for this particular one. And we have tried other applications as well, and it proves that's true. Okay, and the other thing is we actually used, this is depends on what we only show, you know, applications running here is running in minutes. We actually use the full image in net data set, and the longer ones run 48 hours on the smaller number of nodes, and the scaling pattern looks like the trend is very similar. Okay, so that is what I'm going to talk on this. I will ask Professor Panda to conclude the talk.
Yeah. Thank you, Donglai. And so these were all taken, these numbers, just to show you on the OpenPOWER platform, the system called Lassen at Lawrence National Lab. And we have actually one paper, technical paper accepted. There is a workshop in conjunction with supercomputing conference, which will be held next month. We'll actually go into much more details of this design and the performance evaluation. So if you are attending supercomputing in person or virtually, please feel free to join us there. So with this, let me conclude. As we are seeing in the community, we see exponential growth in HPC and AI, and HPC technologies are critical for both high performance applications, HPC, as well as deep learning. And in this context, on the X-ScaleSolutions side, we have 4 products here, very much targeted to the OpenPOWER platforms. And I provided some overview of these products and demonstrated the benefits. And all these products are available if you are interested on an existing OpenPOWER systems or any upcoming systems. If you would like to try any of these packages, please send us a note, and we'll be able to give you a free trial license for you to take a look at it. We can also give you a demo. So this will allow us to get engaged with the OpenPOWER community here, and our objectives are here to make sure that the OpenPOWER ecosystem continues to evolve with high performance middleware for both HPC and AI. So with this, let me conclude here. Thanks for attending the talk. And these are our email pointers. So anytime, if you have anything, please let us know, and we'll be very happy to get engaged with you. So if you have any questions, please let us know, post it on the chat. We'll be here for few more minutes. Otherwise, you can also post it on the Slack, and we'll be happy to get back to you. Thank you.
Thank you.
Are there any questions from anybody?
Not on the Slack channel at this point. Yeah.
Okay. Thank you then. So I'll stop sharing, and then we'll wait for a few minutes before we get disconnected. Thank you. I think we'll get disconnected.